sign-in sheet passed around. One thing I did not give you all last time was actually a hard copy of Homework 6. Excuse me. Even though it's on Blackboard, but I wanted to give you all a hard copy so that you would have it. Let's see. Oh. 1, 2, 3, 4, 6, 7. Okay. 1, 2, 3. There's that. 1, 2. Okay, I think that's good enough. Just I guess pass the extras back up here when you get it. So you all have homework 5 back, homework 6. You have a hard copy. That's due on Friday in the box outside my office. Our next exam is going to be after break, so we don't need to really worry about it. And I'm canceling class on the 17th, so just make sure that your homework is turned in the box outside my office. Okay, sound good? All right. I guess the only other announcement worth mentioning is last time I said there was an event happening on Wednesday in the building. Really didn't know much about it because they just said, so somebody's coming, somebody high profile. Well, they let the bean spill, and it's the governor, so he'll be here on Wednesday if you all want to. There's food, so okay. All right, with that, let's go ahead and get started. So last time, if you recall, you got to watch me have fun with how to do this. So let me sort of full screen that. So if you recall, what we were doing is we were working on shear design, and we were trying to specifically lay out the stirrups for a given span arrangement. Now, here's our shear diagram. A couple things to point out. So we cut our shear diagram off at 25 inches away from the support. And that's the shear value that we use for our starting design. Bless you. Now, we need stirrups everywhere that our shear is larger than PVC, which is 37.9 kips. And we did the math, and we found out that that was around 80.4 inches. Now, excuse me. Another thing that we found was half of PVC, that region between PVC and half of PVC. We don't technically need stirrups from a capacity standpoint, but we're putting them there anyways to just to meet code requirements and to add a little bit of extra safety. We definitely do not need stirrups anywhere past 100.2 inches, which is where the code states we don't need to put any at all. Is everybody okay with that? Now, what we did is we said, all right, let's use a starting S value, or let's figure out a starting S value. Now, our starting S value, we computed that based off of VU star, shear at, shear at D, that 91.04 kips, and we found that the required stirrup spacing there would be 4.66 inches. Now, remember, when you're solving for a stirrup spacing and you've got to pick a value, you typically round down, right? Smaller stirrup spacing means more stirrups, which means more capacity. So the conservative thing to do, like you don't take that and round to 5, you'd round to 4. Okay, you round down. All right, sound good? All right. So we produced a design. Okay. Now we got that was 26 stirrups on one side of the beam. So how many stirrups total? 52 stirrups total. Now, that design, it will work. Okay, I'm not saying it won't work. It will work. But there are some there's some ways we can improve this design. For instance, do we need 4-inch stirrup spacing in the near that region between PVC and half of PVC? I mean, we technically don't need stirrups from a capacity standpoint at all. All we need are stirrups to meet code requirements. So I want to use the maximum spacing possible. So let's let's compute S max, our maximum stirrup spacing. So let's see if we can improve on this design. Okay, has everybody got this? Okay. So let's see if we can improve on this. So all right, so step 3, maximum S value. All right, so apologies if I'm going a little slow. I'm getting over a cold right now, so bear with me. All right, so there are 2 different formulas that we're going to use. I apologize that the maximum stirrup spacing calculation is a little convoluted. It just sort of, it is what it is in terms of the code. So we have an S max 1. Now this one's simple. It's the minimum of D over 2 or 12 inches. Oh, 24. Yeah. Sorry. Thank you. I'm getting ahead of myself is what it is. Yeah. What is D for this beam? Nope. 25. All right, so what is the answer to this going to be? 12 and a half, yeah. And I'm going to underline that just to give me a visual cue. Okay, now that's S max 1. S max 2 is got a little bit more going on. So I tell you what, let me pull that up in the PowerPoint because I think that's going to be a little easier to follow along with what I'm going, or with what I'm doing. So we're computing a maximum stirrup spacing to ultimately improve on our design, and it's the smaller of the following 2 values. So we did this one. S max 2 is a little more convoluted. It's just based on our minimum shear reinforcement requirement. So in order to do this, we're going to have to compute the maximum of 0.75 square root of FC prime or 50, okay? Everybody okay with that? So what I'm going to do is I'm going to take 0.75 times the square root of FC prime and see what I get. So here's what I'll do. I'll say, let's do some calc. So 0.75 square root of FC prime is 0.75 times the square root of what? 3,000 psi. Wait. Do I have this value seconded? Okay. So what is this? Okay, sound good? Okay, now, so remind me, what is the formula for S max 2? All right, so what's the numerator of it's a big fraction. What's the numerator? AV times FY, or FYT. Okay, now the denominator, we have the width, the B, right, times the maximum of that, or 50. So what do we use? 50. Okay, but 50 what? PSI. Okay, that's important, and here's why. So I propose that S max 2 is AV, oh, I can do better than that, A sub V, FYT divided by BW times 50 PSI. So help me out, plug and chug. What is AV? There we go. The units matter. Now, what's FY? No, it is 60 KSI, but what should we use? There we go, 60,000 PSI. Divided by B sub W, and what is the width of the beam? 16 inches. times 50 psi. Again, use your pencil and actually write out psi, in, and then the little 2 above it. I mean, actually write all that stuff out so you can track it. Okay? So if I compute this, what's the units going to be? Inches. It's going to come out in inches. Okay? So go through and do the math. Tell me what you get. 16.5. Do I have a second on that? All right. So here's my two, I guess, those are my two calculations for S max. Now I take the governing value, which is the smaller of these two. So S max is, overall, is 12.5 inches. Now, what I like to do when I lay out stirrups is, could I use 12.5 inches? Yeah, I could use 12.5 inches. I think that's an easy value to use. But I would like to use an even easier value. Keep it simple. So what should I do? 12 inches. Remember, round down. Okay? So I'm going to use S equals 12 inches. Okay, so is everybody with me on that? Okay, now, here's what I'm going to do, and I really want everybody to follow with me on this. Would you agree that if I gave you an S value of 12 inches, you could compute a V sub S? Do you remember how to compute V sub S? It's AV times FY, or FYT, times what? This is the capacity, this D over S, right? Remember that? Remember we have the capacity provided by the concrete and the capacity provided by the steel. The capacity provided by the concrete is 2 lambda BD times square root of FC prime, and the capacity provided by the steel is AVFY times D over S. Y'all remember that? So follow along with me, okay? Would you agree that if I gave you an S value of 12 inches, you could compute a V sub S? Could I then compute a V sub N? VC plus VS. Could I then compute a phi VN? Right, okay. So what I'm going to do is this. This is what I'm going to do. I'm going to say, all right, based on a given S value, let's figure out what the capacity of that beam is, and then let's figure out where can we start using 12-inch spacing. Does that make sense? So I'm going to figure out that phi VN, and I'm going to figure out where that is on the beam, and then that's where we'll start using that spacing, okay? Because I could just put the blinders on and say, well, let's just use it right here, because we know right here we don't need the stirrups anyways. But I would bet we can probably start using 12-inch spacing somewhere back here, and if we can do that, we ought to, because that's going to save us some money. So let's just sort of carry this through and see what happens, all right? So let's determine the range for S equals 12 inches. All right, so V sub S is AV FY D over S. So AV is 0.22 square inches, 60 KSI. Now what was D? 25. Divided by 12, and what do we get? Say it again. 27.5. Do I have a second on that? Okay. 27.5 what? And who said it? Kips. There we go. Okay. So based on that, I'm going to go ahead and compute phi VN, which is phi VC plus phi VS. Okay, so first off, what is phi VC? Did we already do that? think we did. 37.947 kips. Okay, so 37.947. Now, do I do this? Is this what I do? The capacity provided by the steel and the capacity provided by the concrete? And what is phi for shear? Oh, we got to remember that. What's that? No. 0.75. For shear, remember shear, we always have a phi value of 0.75. So, did you say 0.6 for von Mises? No. Y'all remember this? Phi is 0.75 for shear. Okay, so what is this going to be? Say it again. 58.572. Well, you tell me. No, seriously, you tell me. What did we calculate phi VC to be? Yeah. It was like 50 something was VC by itself. Yes. So I could have used the other one and just multiplied the whole thing as long as I account for it. Okay. So sound good? So here's the point. Would you agree that if I use a stirrup spacing of 12 inches, would you agree that the capacity of that beam in shear is about 58.6 kips? Would you agree with that? Okay, all right. My point that I'm making is this. What I want to do is I want to go to this shear diagram and figure out where that is. I mean, this is 91.4, this is 37.9. So what I'm getting at is I can start to use this stirrup spacing probably about, somewhere about here. Everybody kind of see what I'm talking about? Because right here, this is a shear value. Let's say it's right here. This is a shear value of 58.5 kips. From here on, the actual shear that's on the beam is lower than that, so about right here, that's where I can start using that spacing. Make sense? Yes. Oh, we got an equation for it. Remember this? Oh, remember this? We have x at phi Vn, and what we can do is we can say 115 minus whatever that shear is divided by 11.5 kips per foot. Remember, we derived that for this specific purpose, right? We derived that for, based on a given shear, what's the x value? That was the purpose of that, okay? Make sense? Okay, so this is 115 kips minus 58.572, 11.5 kips per foot. So what is that? And that's exactly what I want to hear, 4.91 feet. So that's feet. What's that in inches? 58.88 inches. Do I have seconds on that? Okay. So would you agree that I can start using 12-inch spacing up until about right here, which you're saying is 58.88 inches? Does the scale make sense? That's 25. That's 80.4, so we're about right there. Sound good? Okay. All right. So what we are going to do is we are going to develop a new design, okay? Now, I'm going to literally write it out because I think that's the best way to understand what's going on, okay? So, everybody with me so far? Okay. Does everybody have this? Because I'm going to move on to the next panel. Okay. We should have had a celebration or something. We just hit 50 slides. We just hit 50 panels. Think we can hit triple digits this semester? Well, we might have some hefty stuff coming up. So I'll say a new design. Okay, so I'm going to literally write this out because I think it's the best way to explain it. Okay, so when we lay out stirrups, okay, where did we put our first stirrup? The very first one. That first location, which was about half of the first anchor, so 2 inches, right? So here's what we're going to do. We're going to place the first stirrup, and I'm writing it out, at 2 inches. Bear with me so far? Now, once I get past 2 inches, what's my spacing? 4, because I'm still in that region of really, really high shear. So what I'm then going to do is use 4-inch stirrup spacing and I'm going to use that until I hit what value? 60. How far along the beam do I stop using 4-inch spacing? 58.88 inches, right? Well, okay, I see where you're talking, and you'll see how I handle that here in a second. Until x equals 58.88 inches. And I see where you're getting at. It's not quite 60, though. It's not quite 60. Yeah. And we're ultimately, we'll probably just be able to do it in our head. Okay? Now, once we use 4-inch spacing until we hit x equals 58.88 inches, and then after that we use 12-inch spacing, right? Now we're going to use 12-inch stirrup spacing until when? There we go. There you go. X equals 100.2. There we go. So now let's work on design number 2. Okay. All right. So let's just use some common sense. Okay. So our first one is at 2 inches. So that is 2 inches. Now, how many stirrups do I need to use to get past 58.88? Now keep in mind we're going to be going at 4 inches. Okay, now somebody said 14, all right? So, or 4, oh, got that backwards. All right. So we're going at 4-inch spacing. Let's say that we used 14. Okay, so what's 14 times 4? 56. So that would only get us up until 58, right? We got to get past that. We got to go past 58.88. So how many stirrups do I need to use at 4-inch spacing? 15. Does everybody see that? Does that make sense? So this is wrong, and it's going to be 15 at 4 inches. That will get us to 60. Everybody with me? Okay. So follow along with me. Do you agree that 14 times 4 is 56? Okay. All right. Now, follow along with me. If I start at the very beginning and I use this spacing, where does that get me? Well, I got 2, and then 56. That gets me to 58, right? I can't stop there. I have to go to 58.88. So I need one more increment. Make sense? Everybody else okay with that? Okay, now, so 15 at 4 is going to be 60. Okay, so I started at x equals 0. Where am I at now? X equals what? 62. Okay. Now, x equals 62. I have to go from x equals 62 to x equals 100.2, right? So how far? What is that length? 100.2 minus 62. Say it again. 38, okay? You said 38? All right, now I've got, what's my stirrup spacing in this range going to be? 12. So how many increments do I need to use? 4. I can't use 3 because that's not far enough, so that's 48. What? Yeah, we have to cross that one more. But you see what I mean? All right, so how many stirrups would we be using for this design, at least on one end of the beam? 20. Okay, so 20 stirrups that ultimately cover a distance of 62. What's 62 plus 48? 110. So that's how many stirrups total? 40. How many stirrups did we eliminate? No, 12. So that's 12 stirrups that we eliminated, and that was just one beam. Okay, now imagine if we had 800 beams in a building. Do the math, that's a lot, you know. So getting that one design right, it actually matters, okay? Yes?
Is it possible to space, like, right now we're going 4 and then 12, to space them out even, make them even more efficient beams? So
Oh yeah, we're actually gonna play around with that here in a second.
in between each one.
That's a good point. So what you're asking is, can we literally just like make each stirrup go right where it needs to go? And the answer is yes, okay? But then it becomes a trade-off because now you are designing a beam that becomes incredibly difficult to form. And you got to tell somebody, okay, this one's 4, and this is 4 1/4, and this is 4 1/2, and you know, and then this one comes 5, and you know what I mean? So there is something to be said about, yeah, you want to be efficient, but it's also got to be simple. And there is no perfect answer. I wish there was, but there isn't. I personally would not use 6 different increments of spacing. I'd probably use this. I might use one more, you know, and that's about it. Yes. Yes. Excel. No, seriously. I mean, oh yeah, there is, but you all don't get to use that software until you can do the calculations first. Yeah, there's software for everything, you know. But you won't get to use that until you get out of here. Because us professors, we're mean. We make you do everything the long way first. Spoken like a true engineer. I like it. Any questions? Everybody with me so far? Now, what we've done so far is we've looked at, I mean, let's also be clear, we've really only used 2 stirrup spacings. We've used the 4 inches, which was essentially the minimum, right? I mean, how did we get that 4 inches? That 4 inches was derived by computing what do we absolutely need at the region of the highest shear, right? That's the minimum. The maximum is 12, right? So if we wanted to improve our design, we can really only pick increments that are between 4 and 12, right? Now, I'm of the opinion that the math gets pretty simple if we're using pretty even increments. So I'm not going to use 7 inches. I'm going to keep it simple. Let's try 6 inches. Let's try 8 inches, 10 inches, you know, keep it simple, right? So here's what I'm going to do. I'm going to show you an improved design. You don't have to do this, and I'm not making you do this on your homework, but I do want to show you an improved design. So I'll say additional increments. All right, so we've done 4 inches and we've done 12 inches. So what I'm going to do is this. So we're going to try a few different distances. We're going to try 6, 10, 8, or sorry, I'm getting head, well, that was way off. 8, 10, and 12. Okay, now you know, well, wait a minute. You already did 12. Well, I'm going to show you a really abridged table, and I want to show you where I'm getting that. So, okay, I want to write this here on the bottom, 58.88. Now, I want to talk about these two numbers. So, if you remember, I took an S value of 12 inches. And I said, all right, if I've got this S value, let's compute V sub S. And if I got V sub S, I can compute phi Vn. And if I can compute phi Vn, I can figure out where is that on the shear diagram. So that's where this X value came into play. Everybody with me on that? So that's basically just taking, for S equals 12, like if I gave you an S equals 12 inches, you could ultimately plug and chug and get to here, right? Okay, well what I'm gonna do is this. I'm gonna say if you used an S value of 6 inches and went through and chugged it out, you'd get 37.36 here. And then you'd get 48.12 here, and you'd get 54.58 here. I'm not making you do all that math. I just want you to be aware of how it works. Does that make sense? Everybody okay with this? So I want to show you an additional, I guess, iteration, a design number 3. Here's an improvement, okay? So 1 at 2 inches is 2 inches. Then what I'm going to do is this. I'm going to use 4-inch spacing, okay? And instead of using up here, I used 4-inch spacing until I could start using 12. Like, remember that? I said, let's figure out how many 4s I need until I get here. Now what I'm going to do is I'm going to figure out how many 4s I need until I get right here. And so I do the math and I find that's 9, because 9 times 4 is 36, plus the 2, that's 38. That'll get me past that point right there. That kind of makes sense? Everybody with me on that? Now what I'll say is, now let's use 6-inch spacing. Let's figure out, okay, so I'm at x equals 38. How many 6-inch increments do I need to use to get past that right there? And I will use 4. So that's 24 inches. Then, so this is, so I guess maybe what I ought to do is this. I'll say this is x equals 2. That's x equals 38. And 38 plus 24, that's, say it again? 52. Wait. 62. So now I can use 12-inch increments. I'll use 4 of them. And that'll get me to 110. Okay. So the benefit of adding that additional increment is now I've got, what do I have? I've got 10, I've got 18 stirrups. So this would be 36 stirrups total. Yeah, because if I used 3, that would put me at, was that 56? And I wouldn't quite have crossed that threshold right there. No. Yeah.
Why do we disregard spacing of 8?
No, I mean, you don't have to, but here's my point, okay? All right, would you agree that design 3 was a little more complicated than design 2? Okay. Now think about this. Going from design 1 to design 2, we saved a lot. Like, we saved like 12 stirrups off that beam. From here to here, we only saved 4. If you want to throw an 8-inch increment and a 10-inch increment and add more regions, I mean, go ahead. But are you actually saving on your bottom line? Probably not. Like, you might be able to shave a stirrup or 2 off that, but you start getting into the point where it gets too complicated to erect, and it's like, you know what, let's just keep it simple and stop there. Like, I probably wouldn't go past that, in all honesty. It works, it's efficient, it's using simple spacings. I wouldn't make it any more complicated. Does that make sense? Everybody else okay with that? So that's sort of my, my general philosophy on that. Let me pull something up real quick. If you go to your homework, the homeworks I handed out today, like if you look right here, like problem 2, I said, you know, begin the first stirrup 2 inches away from the support, and then you only need to use 2 increments of stirrup spacing at most, either the spacing at the very beginning and then the maximum allowable. So hopefully that makes the design process a little easier, because the thing about shear design is you all could all use different increments and all get correct answers. And then we got to check through 27, 28 different designs. I don't want to do that. By making these restrictions, it makes the problems a little more doable. You're still doing the same design. It's not like the design got more complicated, but everybody should arrive at the same answer. So that's sort of why I did that. Does that make sense? So I only want you on your homeworks to use the minimum spacing, or the one you need at the very beginning, and then the maximum. Sound good? Yeah, I'm not gonna make it difficult for me on the exam as well. So I'm lazy, remember? I'm a lazy guy. Does that make sense? Everybody okay with that? Okay. All right. Okay. So does anybody have any other questions about this example? I mean, we've produced 3 different designs. Personally, I'd be fine with design 2 or 3. Design 1 is not acceptable. That's not enough. It's enough, but it's not refined enough. I guess that's the better way of putting it. We can definitely take that design and improve upon it. Sound good? Okay. Now, this is example 13. Here's example 14. Example 14 got a lot more complicated, specifically because we've got point loads, okay? So, I mean, how do you think that's going to affect our problem? The shear, okay, yeah. So the shear diagram is going to be more complicated. That's number 1, because it's going to go down and going to go down like that. Now, what were you about to say?
So you're going to need more in those regions because of the jump?
Well, okay, actually, no. What we're going to need is more stirrups in the region of high shears and less stirrups in the regions of low shears. So we might find some abrupt changes to our design as we get into this. So, sound good? All right. Let's at least get our shear diagram constructed and get that started, and then we'll get into the example and the actual laying it out probably on Monday. All right. So, okay. So right off the bat, let's write down a few parameters. Should I put system parameters? What's that? Like, you were supposed to be the guy that tells jokes, Dr. Michelson. That's not funny. All right. FC prime is what? 3. What's lambda? Well, if anything, it was just trying to be kind. Okay, all right, back to concrete. All right, so Fy is 60 KSI. Okay, what's B for this beam? All right, and D value is, all right, how long is the beam? So length is 24 feet. Let's go ahead and convert that right off the bat, and let's get, what is that, 280, what, 288? Okay. Now we've got number 3, U-shaped, or maybe it helped if I actually wrote the 3. Number 3, U-shaped stirrups. So what's AV? 0.22. All right, sound good? Yes, yeah, and if number 3s aren't used, number 4s for beam applications. Now let me say 2 things. Number 1, if you're dealing with really, really high shears like in a bridge, I mean, yeah, you might actually need some serious beams for shear. Like right around the pier location, you can have very high shears and very high moments, and you can have rebar going all over the place. So that's point 1. Point 2, there's actually the option of not even using bars. You could use welded wire fabric. The thing is you have smaller areas, but your spacing is fixed. So you're just picking out a fabric and seeing if VVN is greater than or equal to VU. I don't cover, if you can do this, you can do the fabric. Like this is harder, so that's sort of why I limit it there. Sound good? All right. So step 1 is going to be, just like it was before, to construct the shear diagram. Now, I am not using that line tool again. No. Excuse me. Yeah, I don't know about all that. Ooh. Them's fighting words. I'll remember that. I've got the reach. Is that what it is? All right. The distributed load in this is what, 4 kips per foot? Okay, now we've got 2 point loads, which are about right here and right here. And what are those point loads? So help me out. Does anybody know how we can compute the reactions? Well, we can sum moments, but can we just keep this simple? It's it's half and half, right? Okay. So let's see. So this is 6 feet, 6 feet, and this is 12 feet. So how about this? Would you agree that R is just going to be 20 kips plus 4 kips per foot times 12 feet? I mean, can we just keep it simple? Keep it simple, right? What? I don't do that. I don't do that. Okay, real quick, let's do something real quick. So, because we are sort of running short on time, let's sort of get at least a qualitative image of what the shear diagram is going to actually look like. So would you agree it's probably going to do something about like this? It's going to go up. It's going to go down. There's going to be a jump. And then it's going to go down, right? Now, here's the thing. I really don't care about what happens, out here because it's symmetric. Once I get the first side right, I'm good, right? So let's do this. Would you agree? Okay, that's 68, right? If I do my shear diagram in kips. Okay, now that's 68. I go down linearly 4 kips per foot for a distance of 6 feet. So I go down 24, right? So 4 times 6 is 24. So what's this point right here? Y'all see where I'm doing this? 44. Everybody okay with that? Because I'm at 68. I go down 4 kips per foot for a distance of 6 feet, so that's 24. 68 minus 24, that's 44. So if this is 44, what's that? 24, because I jumped down 20. So this is 24. And then that puts me right here where this is the center line of the beam. Sound good? Okay, all right. I'm going to stop it there because what I'm going to do is, here's the complication. Do you remember when we did our last example, we were using an equation to find x, right? There's 2 equations to find x on this one because there's 2 lines. We will attack that on Monday, though. That's all I got. You all have a fantastic weekend. I will see you on Monday.